Hi. In this talk, I'm going to present a new algorithm for solving slope. This is joint work together with Quentin Klopfenstein, Matthew Messias, and Jonas Wallin. The problem that we are tackling is solving slope, which is a sparsity-inducing model with appealing properties, but for which the best algorithms, at least up until now, are considerably slower than solving, for instance, say the lasso. And our contribution is a new algorithm which improves upon previous algorithms, and it is a combination of proximal gradient descent and coordinate descent. Slope is a type of penalized regression that consists of the squared norm of the residuals and a penalization term, which is the sorted L-One norm. The sorted L-One norm consists of a non-increasing and non-negative sequence of penalization weights, lambda, and it aligns the weights in the penalization term so that the largest of the lambda is associated with the largest value in magnitude of the betas. In other words, it penalizes the largest elements of the coefficient vector the most. It's actually a generalization of the lasso, which you get if you set all of the lambda equal to the same value, as well as the L-infinity norm, which you then get by setting the first element of the penalization sequence equal to something larger than 0, and the remaining ones equal to 0. Slope has appealing properties, and one of them is clustering. If you view slope as a constraint problem and look at the constraint region for slope for the sorted L-One norm, you can see that solutions for slope can either lie anywhere on these edges or at the kinks of the ball. If you are at any of these kinks that align with the axis, then you get solutions that are similar to the lasso in that you get a sparse solution. But if you end up on any of these kinks, then you actually get clustering. So the coefficients of your solution are set to the exact same value in magnitude. And in this case, they're actually set to the exact same value. So beta 1 and beta 2 are set to the same value here. This clustering typically happens when you have large correlations between features in your design matrix, or if the coefficients are very similar. And this is a nice property, particularly if you compare it to the lasso, for which you can get solutions where either of two features that are heavily correlated is dropped entirely from the model. Slope also is able to control false discovery rate, recover sparsity, and ordering patterns of the solution. And in addition to this, there's also a convex penalty. So you have a unique solution in unique minimum, unlike, for instance, MCP, where you don't have that because it's a non-convex penalty. So you may think that slope would be immensely popular given all of these appealing features. But it turns out that the lasso still is much more popular than slope, which you can see, for instance, from the download statistics on Crayon for the GLMNet package, which is the most popular package in R for fitting slope. The lasso, and slope, which is a R package for fitting slope. You can see that the download statistics for slope are being dominated by those of GLMNet. And one of the reasons for this discrepancy is that the state-of-the-art algorithms for solving the lasso are significantly faster than those for solving slope. For instance, solving the TCGA dataset with a slope takes 43 seconds, and doing the same for GLMNet for an equivalent problem, as close as you can make one, it's 0.14 seconds. So there's a large difference here, of course, and part of the reason for this difference is that you can use coordinate descent for the lasso, which has turned out to be extremely effective for many problems. For example, these two problems for the use 20 and RCV1 datasets, we can see that using coordinate descent, we basically dominate accelerated proximal gradient descent in this case, when fitting the lasso. Unfortunately, It's not possible to directly use coordinate descent for slope because of the fact that the sorted L1 norm isn't separable, as you can see if you consider the penalization term, the norm again. And you can see this. You can see an example of this in this two-dimensional example of slope, where we are at this iterate, this point during optimization, and our goal is to reach the optimum over here. And we're optimizing using coordinate descent either over beta 1 in this direction to be precise, and over beta 2 in this direction. You can see that if we move over beta 2, you can see the function value over here. You can see that we are already at the minimum, so there's nowhere to go for beta 2. And moving along beta 1, you can see that we have the same situation. Basically, we are at the minimum over here. We can make no progress. What we'd ideally want to do here is, of course, to merge the two clusters together and move them in unison over towards this optimum. But a direct and naive coordinate descent approach cannot do that. If we were to know the clusters in advance, then we wouldn't have these problems, because we could reformulate the problem so that it becomes separable, conditional on the fact that we know then the identities of all the clusters, how many they are, and also the signs of all the coefficients inside the clusters. Then we could just solve it using coordinate descent. That's of course not possible, but our idea is based on using proximal gradient descent steps to identify this structure, these clusters, by a property of slope called partial smoothness, and then use coordinate descent steps in tandem with these gradient descent steps on the clusters, so that we can converge fast but also find the correct pattern. And our algorithm in its basic form looks like this. Every vth iteration we take a full proximal gradient descent step, and what this does, it allows us to find the correct pattern. It allows us to find the sparsity pattern and the clustering pattern of the solution, which in other words allows us to both split or merge clusters. At all other iterations we take a coordinate descent step on the clusters. This step allows us to actually merge the clusters, but it cannot split the clusters. And the algorithm can be viewed as a hybrid then of coordinate descent and proximal gradient descent. So if we were just to use coordinate descent, starting at this point, you can see that we make fast progress towards the optimum. In one cycle we move over here, then another cycle, end up here, and we move both coefficients as one cluster, but then we are stuck using the coordinate descent steps at this point. To proceed towards the optimum, we would need to split this cluster. For proximal gradient descent, on the other hand, you can see that we reach the optimum, but we approach the minimum much slower than we do using coordinate descent. And our hybrid method, it interleaves these two steps. So it starts by taking a proximal gradient descent step, then it proceeds taking a few coordinate descent steps, converging quickly. But then at this point, where we were stuck using just coordinate descent, we are able to take a proximal gradient descent step, split the cluster, and converge towards the minimum. When updating the Kate cluster in our solution, we introduce this notation and view the optimization problem as a problem where we modify the coefficients of all the features inside one cluster, but keeping the relative signs fixed. So we modify the coefficients of the clusters in one go, in tandem, but we make sure that the signs stay fixed. And this amounts to solving a one-dimensional problem, where we end up with a different penalization term that we call the partial sorted L1 norm, and which looks like this. So basically it is similar to what you would see for the lasso, for instance, when solving a one-dimensional problem for the lasso, but you can see that we have kinks here at the locations where the coefficients of the other clusters are. So as we increase the value for the current cluster, you can see that as we reach one of the other clusters, the gradient of the penalty here increases. And now, how do we then solve this minimization problem? We can use the directional derivative, which is visualized in this plot over here. And the optimality condition to the directional derivative in one dimension is that it should be non-zero or larger or equal to 0 for any direction, which in this case, since it's a one-dimensional problem, is either 1 or -1. You can see that for this particular example, this occurs at this point, where we have another cluster. So this has a direct form, an explicit form, which you can view using what we call the slope thresholding operator to make a connection with the soft thresholding operator for the lasso. And if you are familiar with the soft thresholding operator, you know that it looks like this basically. You have a straight line that approaches the point at 0 here, and then stays at 0, and then continues as a straight or as a linear line. But here we have instead steps in this thresholding operator where we end up with clusters. So input to the soft thresholding operator means that it reaches a point where small changes doesn't make a difference to the solution. We're just still staying in the cluster until it becomes strong enough to escape the cluster. Looking at the experiments of our method, we see that we do very well. Our method here is in green. In general, particularly for low levels of regularization, or for large levels of regularization, where we often beat the competition by large margins. In particular, we, in our method, always do quite well, even when we are not the best method. The oracle method here is the method, the dashed black line is the method where we assume that we know the identity of the clusters when fitting the model, which is of course not a real situation at all. It's just added here for us to be able to see basically the best case solution that we would be able to get with our method. Despite this, we actually see that we are actually sometimes even able to beat this method. And we see similar situation here for simulated data, although we do even better in this case actually. Here we have 3 different setups. Simulated 1 and 3 are both high dimensional setups, but simulated 3 is a sparse setup with a larger number of features, and simulated 2 here is a non-high dimensional, so low dimensional setting where we have more observations than we do features. In any case, we do very well, as you can see. To wrap up, we have presented a new algorithm for solving slope using coordinate descent and proximal gradients descent in a hybrid scheme. The experiments in our paper, in our work, were conducted using BenchOpt, which is a framework for, in a transparent and collaborative fashion, comparing optimization algorithms. And the code is available open on GitHub at this repository. And we invite you to, if you are conducting research on slope, add your own solver to the BenchOpt benchmark repository over at this link. Thank you.